Today's topic is axial tension and compression. We'll go through 3 statically determinate examples. This is second from 3 examples. A 2-stage rod has been permanently fixed at end D and loaded with forces P and 2P, as shown in the figure. Calculate what the value of force F must be for the total elongation of the rod to be 0. That is delta LC. Delta LC total is equal to 0, and force P, Young's modulus, and the diameters of these 2 sections are given. Well, so we write out the forces in the sections, as in the previous example. I'll now mark them AB, BC, and CD. So the force in section AB, looking from the right side, we don't reach this force P yet. It's positive F in line with the sense of direction of the x-axis. Positive F. Second section, force in section BC. We look from the right side and we have F minus P. We don't reach this force 2P yet, we're infinitely close to it, but we don't see it yet. We only see it in section CD, so we have F minus P. And in section CD, we now see all 3 forces, so we have F minus P, add 2P. Finally, F plus P. And we'll also do the ratio of the cross-sectional area AB to the cross-sectional area BC. Well, it will make calculations easier. We can write that the cross-sectional area AB to the cross-sectional area BC is, and we'll express these areas, well, as pi d squared fourths, so in a notation with diameter. Well, the area of a circle is pi r squared. And if we substitute d halves for r, we get pi d squared fourths. So the cross-sectional area AB is based on diameter d2, so we have pi d2 squared fourths. The cross-sectional area BC is based on diameter d1, pi d1 squared fourths. Multiplying by the inverse of this denominator, well, pi fourths cancels out, and we're left with d2 squared over d1 squared. So 15 squared over 20 squared. Which gives 9/6, or 5,625 10,000ths. We multiply both sides by the cross-sectional area BC, and we have such a ratio, and it will be convenient for us to calculate further now. The total elongation is the sum of elongations of successive sections, so delta L total is delta L from section AB plus delta L from section BC plus delta L from section CD. We recall the formula for elongation. It's the force in the rod times the length of the rod, or section, divided by Young's modulus times the cross-sectional area. Well, and we substitute the forces from the sections. We have the lengths marked in the figure, Young's modulus and cross-sectional area. So the force from the first section, F times, the length of this section 4m, divided by Young's modulus, which doesn't change. And here should be the cross-sectional area AB, but I know that this equals such a part of the cross-sectional area BC. So I've already substituted here. Well, and further the same. F minus P is the force from the second section times 3m length of the second section. And I substitute all these values into the formula. Then I multiply by Young's modulus times the cross-sectional area BC. The denominator cancels out for us. We're left with this much. We arrange it. On the left side, we leave factors with F, on the right side with P. P is given in the task content. It's 15 times 10 to the 3, so 15 kN. I divide it here by what stands next to the unknown F. And finally, I have that F equals 2.7 kN. We can do a check. Whether indeed if we give this force F 2.7 kN, then the total elongation will be equal to 0. Well, and it turns out that due to these roundings that were used here, even with this ratio, maybe not yet, but here 2 divided by 11.11. Here, a rounding has already appeared. So let's do a check. In the check, we substitute for the force NAB. This calculated F, so 2.7 should be here. There's a mistake, 2.7. Everything in basic units, so times 10 to the third, times 4 meters. Well, and we're already substituting the numerical value for Young's modulus, 2.1 times 10 to the 11. The area of section AB is pi diameter of section AB squared fourths. And so on, I substitute everything. Well, in substituting all these data into the formula for total elongation, it turns out that we get minus 6.17 times 10 to the minus 9. So it's not 0, but it's a very small value. It's not 0, because it results from this rounding that was applied earlier. At this point, if we had designed the task in such a way that no rounding would appear, then in this check we would get exactly 0. Well, and because roundings appeared, it turns out that it's a value times 10 to the minus 9. Very small, minimal, so it's about 0. Due to this rounding, there's this small, minimal inaccuracy here. If you have any questions about the solved tasks, I encourage you to ask questions under the video. I'll try to answer. I also recommend our other productions. And that's all. Goodbye. Greetings. Bye.